Thank you. Can you hear me from the back? It's good. Yeah. Thanks for the introduction, and thanks for inviting me here. This is my first first EGSR ever. I'm really enjoying it so far. I'd like to thank Abhijit and Tobias for this amazing organization and making sure everything's running smoothly so far. Okay, so today I'm going to talk to you about rendering. No, that's not the plan. I don't know much about rendering, but I'm going to talk about generative models, and I'm going to talk about certain aspect of the generative model. I'll go into certain level of details, and I'm hoping that one of the two things would happen. That you would either get very excited about this and come and help and solve the problems there. The other thing, which will also be very cool, is you can bring your knowledge of rendering and solve some of the problems we are having right now. And I'll point to those as we go. Okay. So that's going to be the talk. So first part, I will talk a bit about generative models in the case of diffusions, and then I'll talk about a few use cases. And I'll try to answer this question, like what are good representations for these ones? And no surprise, there is not going to be a magic representation. The answer will be, it depends on the context, and I'll show you 3 different representations that are useful. So what is the main problem we are trying to solve? This is a slide I borrowed from Andrew Price, which is showing the problem like generative just content generation in the digital world is expensive because of multiple stages. Creating the concept is expensive, creating the mesh is expensive. My background is from geometry processing, meshing. That part is expensive. Creating textures is expensive, creating the final pass rendering expensive. So you know how this is, and this is for a single object. When you add it up, it quickly goes up this number, right? And now everything is still static. Imagine things start moving around, this quickly becomes not very tractable. What we know so far is we know the forward process. We, as in you guys, know, and I know some of the people whom I can ask how to do it. Where if I'm given a geometry with all the material descriptions, I can come up with this image. Right? This is very good. So that's the computer graphics we teach. That's what we learn. But I want to say something which might be a little bit controversial to this audience. Is if my end goal is this image, there is another workflow, and I'll try to convince you this is the case, where we don't have to create all these detailed meshes, appearance, etc., and we still get the same quality end result, in certain cases, better quality. Right? And what this allows us is to get away with worse input. And this is often the case because this will allow us to avoid solving the inverse rendering problem, which many of you are trying to do. We know that inverse problems are generally hard because inverse problems are often ill-posed. You have to bring in priors. But for certain scenarios, it is possible to get this end results without doing the full explicit forward solve. And that's the one I want to solve. This is not a vision I had like yesterday. This is a problem I've been working for a long time. So this is a paper we had from 2012 where the goal was, given a single image, what type of changes I can make to this image. And I'll just show you the results. Okay. So the goal is, how do I analyze the image, the underlying scene of it, so that I can learn certain aspects of it, so that I can try and manipulate this image as if I had the 3D world, but I'm avoiding building the explicit 3D world. That's hypothesis. Now, when I look back, it looks like just fake, because many of them are fake. And the reason is most of the steps were done with classical geometry, like you have a box, you do some texture mapping, you do some fake shadow, etc. And with these new tools, you can revisit the same concepts, and some of them are much more solvable now. And I hope in the next hour, with the next 50 minutes, you will partly be convinced that this is possible, or we are getting to this thing. The first time I thought this is possible was not at this time, but a few years later, maybe about almost like 8 to 10 years later, when we saw StyleGAN. So you saw StyleGAN 2, these are the type of images. And we worked on a problem where how do you navigate the StyleGAN 2 space for doing edits. And this ended up in Photoshop. Unfortunately, the things moved so quickly that within a year of introduction, we have a new setup of tools available. But this exists in Photoshop in the neural filter as well. And here we are showing certain directions in the StyleGAN space where we have edits in terms of lighting changes, and you see also camera changes and other things, right? So this all exists in this latent space, and we are trying to just extract this out. So this got me thinking, like, do we really need 3D? And this is a question that I still have in my mind. Please don't ask me at the end of the lecture if this is true or not, because I still don't know if we need 3D. So after GANs, there entered this new generative model, which is, as you know, is this diffusion process, which is not a new process. It's if you look back in how this was done, it was the original results. The earliest I know is from 1970s, where the guys at Stanford Statistics Department were studying these processes, and these suddenly becomes quite useful. I will try to go in a bit more details of this because I think this is going to be useful to explain some of the concepts or what I think I have extracted from this material in this last couple of years of learning. So the main goal is to sample from an underlying distribution where the distribution is unknown. This is the goal of generative model, right? This is period. Where a point is an object. Of course, if you are doing machine learning, you have to start with cats. So here we have an image of a cat. So each point in this space is here, and what we're trying to do is we're trying to do what is the density or probability density of this point in this unknown manifold. And if we can create this manifold, then we can sample from this distribution, so all good. But the only distribution that we realistically know how to sample in very high dimension is a Gaussian distribution, right? So the whole problem is I know the right one, I want to do left. How do I do it? So instead of trying to learn directly the distribution, we try to learn a change of variable, which is the mapping between the two distributions. And this is the unknown map. Once we can solve this unknown map, we can do unconditional generation by sampling. So this is all good. And this is a process we have heard some very nice summaries yesterday, how this is done. In the forward process, we start from a signal, which is a cat, and we progressively learn this step because a single step is very difficult to learn. It's a difficult path in a higher dimensional manifold. So we break the difficult problem into many small steps. All these steps are modeled, and this is a choice. I modeled each of these transitions is modeled by a Gaussian distribution, as you'll see here, where this Gaussian distribution, the beautiful thing about Gaussian distribution is if I know mean and variance, or mean and covariance, I know everything that I need to know about it, so that helps. And there are really pages of known results of how to mix Gaussian, what happens, the end results Gaussian, etc. So this is good. But the only thing I need to know is mean and variance, and the mean is defined as some function of the previous image, and the variance is fixed. This simplifies a lot of the calculation. Nice thing if you do a bit of unrolling is if I have to do a map across multiple stages, I can either take this many small hops, which are learning a complicated path by taking small steps. You can unroll it, and because it's Gaussian, when you convolve them, it's still a Gaussian. End result should not be surprising that you can take the long hop in this direction, and again, it's a Gaussian, and it's, again, a formula that relates the mean at time 0, which is the starting signal, to the mean at time t. So there's one relation that comes up. I want to highlight 3 things here. So there's various constants that you can look up if you have to implement. That's not so important. But the most important thing is this long yellow step. So starting from the original signal, how do we get noised signal at some time t? This can be done in one step. And this relates these 3 quantities. The noise at time t, which is, the signal at time t, which is at xt. The original signal, which is x0. And epsilon t, which is the noise we add at time t. So these 3 things are related by a linear equation. So if I know 2 of them, I can always express the third. remember this. But our goal is to go from the right to left, because eventually I want to do the sampling. Here the story is not so nice, because this mapping turns out to be much harder, and it's approximated each of the steps. Again, I repeat, it's approximated by a normal distribution. And again, if it's a normal distribution, I need to know only mean and variance. So the only thing I need to estimate is the mean, right? Because variance again is assumed to be constant in this formulation. And again, we can find this based on this relation. Like if I know 2 of xt and x0, I can find. Okay, so far so good. So let's look at this in some form of a diagram, what's going on. I start with a signal, x0. I add noise. I get the noise signal. This is my xt. And then all I have to do is to predict this denoising network, as we have already discussed yesterday. So this denoising network gets a time index t. So it knows which step it's trying to denoise. This is important because that way I know how much noise was added to that. This is super important. And there's a bunch of conditioning. I'll see this later. This denoising network has been realized mostly by a UNet because Stable Diffusion has this. More recent version has DIT based, but that's for a future discussion, not for today. One question is, what is still the loss that is optimized for this getting? So far, so good. There are 3 interpretations for the loss, or 3 ways you can do. The first one is I can predict you can make the network to predict the noise. This is the epsilon t formulation. The second one, you can predict at each step the x0, the original signal. And this turns out to be quite important for many of us in graphics because this is much easier in many of our scenarios. To this. And the third one goes to score-based formulation. There's another sort of a maximum likelihood-based scoring, that type of approach. Now, the derivations for each of them is very nice, and I would encourage you to at least once try to follow this. It's really possible to follow, but I don't know how they came up with it. It's much more difficult. The good news for us is all 3 are equivalent. So you can do any of them and get the same answer. In theory, although the second one sometimes is more numerically stable. Okay. So that's the background for this diffusion part. Now there's 2 more things I need to explain. One is in the original pixel space, this is a very high dimensional space, so things becomes very slow. So what people have done is they have first created a latent space and do this whole process in the latent space. And this is the latent diffusion model where instead of doing x0 and xt, you do z0 and zt. So this is in the latent space. And this is what most of us use because this was used in Stable Diffusion. This is what it's trained. One thing that's good to know is, although this is trained as a VAE, etc., the actual encoder-decoder in Stable Diffusion is pretty close to a linear map. So you can reuse this encoder-decoder in many other scenarios, even if these are not RGB signals, which happens to be quite a useful thing. The last thing I need to explain is a bit high-level intuition of what this attention is, because I'm going to use it. This is not about whether you're attending this talk or paying attention. It's really about attention. It's actually a very simple concept. So we have 3 quantities, a query, key, and value. So query, key, and value. So query and key, right? And based on the similarity between query and key, I can pick which rows of which values to use. It's very similar to if you have a database of entries and I give you a new entry, you compare to each row which ones are similar and pick the corresponding value. Right? So the similarity is computed many ways. The most standard one is using a dot product. Hence you would see a Q dot K matrix that is exactly doing this dot product. And based on the similarity, you select the value, which is V. This product, Q and K, is called the attention mask, which has implications as I will use in the talk. Okay. these output is called the feature, the combined one. It's also called activations in this sense. There's lots of tutorials available online. You are welcome to look at these. These are the basic algorithms. You can look at our Eurographics course or come to our SIGGRAPH course to go into details of this. So that's all I will use for this one. Okay, so we learned about this, so we were quite excited. We said, okay, I work in 3D generation. Let me go and solve 3D generation, 3D model generation. These are two papers we presented last year, both at CVPR. I understood in the town hall that you guys are not a big fan of CVPR, but we still bring it. And you will see why, because these are the results, and these are state of the art, which I don't think will fly well if I tell you these are state of the art at EGSR. Because these are, come on, these are like tiny images. They don't look anywhere close to the quality of images we can produce. These are 3D models that comes with geometry and texture, but not in form of mesh and texture map, but something a bit more abstract in terms of features. The advantage is these can be trained with 2D images. So we were very proud of these results, and we are still very proud. But if I look from an artist's point of view, there's two things I am missing. I don't have control. These are uncontrolled generations. And the second thing is they just don't look good enough. So what do we do? Now, here's now the problem that comes in. The problem in the 3D world, we don't yet have scalable ways to get 3D content at a huge volume. Okay? So we look back and we looked at what this image guys are doing, an image and video, and you look, this is the quality you'll get. Right? And you can try yourself right now, and you can do this. If you go to video, it becomes a bit more control. And they have controls in the form of control net. So from here, you can give mask, and you'll get really nice images. People have also used, and some of you in this audience have done, use this diffusion model as a renderer to get renderings on the right. Okay? So we saw that, we said, okay, we need to change our research plan. It's not going well. So we focused on how can we understand this and use it in our context. Remember, the goal is to be able to create somewhat close to these images with certain level of control. And again, the goal in the remaining is I'll go and focus on 3 tasks: generation, analysis, and editing, and I'll go into details of them and show that in these approaches, there are different representations that come out to be handy. Okay? So in the following, I will talk about 3 projects. In each project, I will, of course, show some results that I think are cool, but I will also try to give you some intuition that we believe, which I think is true, which you may not get in that form when you read the paper. But again, take it with some grain of salt, because one humbling experience I had so far is sometimes in this world, we believe I understand something, but in a few more months, I realize it's not the case. Because it's such a nonlinear manifold, it's very hard to be sure what we have is the right understanding yet. And I'll explain this a bit. The first one is what we have, this loose control, which we are presenting at SIGGRAPH later this month. So the goal is to create images, but I am a very poor 3D artist, so the level of control I can do is, this is the level of complexity I can do of creating a tree. So that's supposed to be a tree on the left. And the image I want to generate is the image on the right. Okay? So that's what we want to do without having to do all the geometry of the tree and all the appearance or the lighting, etc. And there is this tool that you know is ControlNet that allows you to do this, where you can have a stable diffusion or a trained image generator. You can give it a very limited amount of paired data, and yesterday this was nicely explained in Johan's talk. And then you can train this, right? Like what happens in the original control net is there is this depth-based control net among the many others that are available, where if you give it depth, and this is the top one, so the depth, I'll wait for you a few seconds to imagine, but they are may not be clear because I didn't give any context, but these are the corresponding images they will produce. Okay, so now I have a way to go from depth, which is on top, to this bottom. Right? So seems like we're done. Right? Unfortunately, for many of us, creating the top row is as hard as creating the bottom row, or at least almost as hard. Right? Because how do I create anything of that complexity unless I can scan? But that's not, in a generative world, I cannot really scan. So what we want is more like partial guidance. I want to specify roughly blocked thing. Again, think of the interactive images I showed. That's the level of control I will have. And I will say, oh, these are in a living room with a couch, and this is the type of result I will get. These are animations, but think of static frames of this, any frame of this. So I want to give specification at the level of the left and get something on the right. So how do we enable this? So this is for indoor, same for outdoor, and again, this is the level of complexity. Okay. You will already see there's some appearance continuity in between. So can we not do it with control net? I know there are some experts in this room. There is a control net parameter that you can use. And on the top right, just if you see here on the condition, we specify a depth map, which really gives the 4 walls. So if you were in this corner, this 2 walls and the roof and ceiling, that's what's given. If you do this, and even if you change this parameter, it will give mainly empty rooms, because that's what it has been trained with. So this is not incorrect result. This is what it has been trained to do, but that's not the type of results we would want. We would want what we see on the bottom, that it does conform to this specification, but also fills in the room in some way. In graphics, we like masking, so can we not get away with masking? And people have tried this. So if you are given a room where I want a sofa in a 2D space, but not in a 3D, that's indicated by the red one. It is possible to restrict the diffusion process in there to generate a sofa, and you can get a result like that. But as soon as we have cluttered rooms, this doesn't work, because I cannot do complicated depth ordering, etc. in a cluttered room here. I'm not explaining these results here. But if you do with other hours, in 3D, these occlusions are not a problem, and we can get generation just here. Okay? So how do we do it? So if we are to use control net, we have to get some sort of a paired data, right, to train it. Now the paired data I need for these images, indoor or outdoor, is some sort of a proxy depth. And the proxy depth I would need is here. So the question is, how do we get these type of paired data? Now, I would explain what we did, but I will explain what is the first thing we did. The first thing we would try to do is, can we not do with synthetic data? And we went down that path because we have synthetic data, we can do that. But then, as I'll show later, it doesn't translate to real world images anymore because there's immediately a gap. So what we do is we fall back with our geometry background is, can we not work with estimated depth? And it turns out like we luckily worked on scene understanding for 10 years, so we knew how to do this. So you can go from this image, you can extract the depth. Scene understanding with respect to rooms are quite simple, because then you can take the depth, project it down on the ground, and you already get the walls quite reliably. You can extract it, and I can get back these walls. Okay? So I can use that to create some plane estimation, get the paired data. So now I can take lots of real images and generate their paired data. Now, you know how depth estimation works. They're not very good, right? But that's fine, because I'm going to train with the type of errors that I will have on the real data. So that's a very important thing to remember if you're trying to set up such a thing. For 3D box, it's also same. Now I have the ground. You can also extrude them to have boxes, and I have this paired data. Okay, so now I have paired data. It's imprecise, but the type of errors I have is the type of errors I will have in practice. So what I can do is I take this and train this adaptive layer with the paired data I have. And this is trained with a low rank approximation, which is a LoRa, which is a way of reducing, giving less capacity to the network so that it doesn't overfit. There was a question in yesterday's one of the talks, like what happens if we train more? And I think this is a very good insight to have now. So if we train very little or too much, then we both are problematic. So if we train too much on the synthetic data, not in synthetic, it is extra data, then we can go outside the biggest set of images it has been trained with. So that's a problem. If we train too little, it doesn't conform to the depth. So there's a balance, and this is unfortunately done manually instead of training. Right here. There's some scheme you can have, but this is roughly the case. Now, I do want to point, because I had a discussion with one of you yesterday on this one, like this question of refining the control net. Essentially, we're optimizing on a very limited data, and it is a characteristic of the problem itself. If my original solution is very far from where I want to be, it's unlikely this little data will get me there. So you want to be as close as to the solution here possible, and this is the way we encounter with this estimated depth is a way to get close to this. In hindsight, it's an obvious one, but we wasted 2-3 months going down this track. So maybe you can save yourself some trouble if you have to do it, something in your domain. So how well does it work? It works quite well, and I'll show you some visuals. But of course, we did evaluation on multiple things. I just not go into the numbers, but I do want to mention what are the attributes we compared against. One is we want to see how well they align with the original text. The clip column. This blue one is, again, another way of checking text and image alignment. And the third one is how well it conforms to the condition. It's easy to remain very good in terms of images, but completely ignore the condition or give very fake images exactly the condition. You want somewhere in between. That's what we do. Okay, so that's all the hard part done, and we can look at the results now. So always on the top, I will show you the specification. This is like 2 walls and 3 boxes, and the keyword is panda, and we can now do some here. If I had shown it as a GIF, you would see some flickering because this is not consistency here. You can also edit an image and generate it, and I move this so far or rotate it, and you'll get these ones. Okay. Again, always try to think back of the goal we have. How much would it take to create this model, both the geometry and appearance and render, and try to do these edits. You can also do more abstract edit because we are working in the latent space. So we can say make the room more populated. So on the right, here, again, more populated, or for individual objects, you can find more interesting attributes. And in all of them, remember, we are using a diffusion process, so we have a space that we have rather than a single solution. And these are showing kind of PCA axis in these directions, in these spaces. Okay. PCA in a very loose sense. I want to highlight the limitations. So we have this notion of primary and secondary object, and this works with this primary object. We don't have control on the smaller things on the table, etc. But it's not something that can be addressed easily. Because if you think of the method, as you give more and more constraints, then the diversity of the results will shrink. So this is not something that would work out so easily. Which is the same, we cannot get very precise alignment between text and 3D. And any sort of bias and others in the data set, in the stable diffusion train, that will be inherited here. Okay. Good. So here was an example where we focused on generation, and for generation, the good representation where this just really blocks. And there's a recent paper, I think it's called Coin 3D or so, that has blocks for the individual parts of an object or a humanoid, and you can also do the same thing. Right? So this is good. Like from coarse object modeling, you can get a final image. So that's good. One nice thing about these generative models, especially in this diffusion one, is because we work with a distribution, it already gives the analysis part as free. So let me explain what it is. in the sense, before I used to take an image, I used to construct a scene and then do analysis. But in the generation process itself, it generates certain features that I can repurpose for analysis. And that's quite a new thing for me. And I'll explain this in the next part. The next goal is a very classic geometry processing problem. Like if I have lots of shapes, here's a single shape here, I want to bring these shapes in correspondence. So this can be this person, but this can be all this person in a different pose, but all these other things. And here I'm already showing the result where same color indicates same path. Now this is a very, very well studied problem in geometry processing. If you go to the SGP, which is the counterpart of this symposium in the geometry world, you will surely get half the papers focusing on this problem. So what's there left to be solved? It's a new source of information that you can use to solve it. Okay. Now, how did people solve this? So there's various problems. One is a mesh, another is a point cloud. How do we do this? One is it an isometric distortion? Is it like a conformal distortion, et cetera, et cetera? Or is it a semantic correspondence across very different things? But the fundamental problem is somewhere orthogonal almost. Like many of the meshes, when we look at each of these meshes, let's look at the human, I immediately see and associated it with the human. But if you look at the mesh and the triangles, there may not be a feature for this maybe junction, or there may not be a feature for the ear, etc. But this is a semantic feature that we visually associate, but not there in the mesh. So no matter what algorithm we use, it's hard to extract it from here. And that's what we will try to extract. So just to summarize the different axes we have, we're not going to use any training data here, and it will go handle all sorts of meshes, as you will see, and it'll also handle point cloud. It's not going to be supervised. So this method, the loose control, was partly supervised with this fine-tuning under ControlNet. The next two, this one and the next one, there's no additional training. So it's training free after stable diffusion has been trained. So it's a bit of cheating, but no further training, let's say. So ours will, of course, have all things. That's how we design these tables. But the main thing is there's no extra 3D training data and no extra supervision. So if you look at the image world, these are the type of images that are generated by Firefly or any other top generator. And as it has been shown, this is not us, previous results have shown, that they carry semantic features. So I can click on eye of this boy and it will map to the eye of the eagle, etc. So these type of correspondence can be found. The problem is when we have meshes, we don't have these characteristics because this is the most common type of meshes we have. So how do we use the richness from before? And I'll explain how this is done. And one shift in thinking is again a takeaway that you want to remember. The diffusion processes are great as a generative model because it models a distribution. It's not a single observation, it's a distribution. So we have to think, how do we compare distributions, etc. Like you have been working on sampling, you will never compare one sample directly with another, you will compare the underlying distributions. And that's the insight that we will use here. I'll first start with the result. So between these two shapes in arbitrary poses, I just show them in same poses. Same color indicates correspondence. And this is quite a strong result because it can distinguish, in this case, left and right, which is quite a difficult concept if you are going based on the geometry side. So how do we do this? How can we solve this problem? So we start with the object and we render it from multiple views. And what are we rendering? We already studied ControlNet a bit. So I render for each of the camera, I render the normal map and the depth map. That's all I do. And then I render through ControlNet. So I give a cat keyword. Okay. Now, if you look at this, I'll give you a couple of seconds, you would notice something odd, and this is expected, that these 4 images of cats or this 100 images of cat, they're not the same cat. Yeah? Now, our first reaction is, okay, can we do some optimization to make it the same cap? But this will be wrong. Because again, remember, these are each samples. So we want to work in the distribution rather than average it out. As soon as we average it out, we have lost certain information. So don't average it out. Okay, so we want to work with these textured images, but not in this level because the textured images output here. I want to work in this intermediate layer which still has the higher dimensional features, and that's where we work rather than extract to RGB, because our goal is not RGB, our goal is features. Okay, with that intuition, now I have to do two things. Where do I place feature points, and what are the features? These are the two problems. First thing I can do, I can leverage these image diffusion models to find good locations, and this is where Dino Features does. It's a type of image feature. What it does is, these are semantic ones, so they will trigger near eyes or near nose or near other things, right? So that's good. And they will be all consistent because even though these four images are different, the eye locations are the same because they are all linked to the original 3D model. So the locations will be consistent, so that's good. And then what I do here, and I will say a little bit here, is we take the diffusion features. And if you remember the part where I explained attention from this Q, K, V, so it's really the Q and K, and that tells me what values it is. And then I do the V and get the final activation or feature. That's what being read out with some multiple levels because they come at different resolution, which in the diffusion world correspond to different time zones, or time steps. Okay, so now I have location and the features. I can fuse them and project it back onto 3D because I know the rendering. Okay? So what did I do? I took the original mesh, went through this process. In the end, I got locations stuck on the 3D, but it has features. It looks like the features are three-dimensional, but actually these are much higher dimensional. This is 1080, I think, because that depends on the features I copied from the orange one. Okay? And this turns out to be, you don't have to do anything else. You take these features and do nearest neighbors with them, and I'll show some results. It gets close to state of the art, if not like sometimes beyond state of the art. So the intuition for this part is the representation is don't project unless you have to, because as soon as you project, you would lose the information. Keep in the distribution sense as much as possible. And for this application, this turns out to be good. So here are dense features, so you can get very dense features this way. So this is humans in different poses, also in different shapes. These are not all isometric because our body proportions are different. You can go across like more abstract ones, and you see the neck of the cow maps to the neck of the camel, and it gets stretched out. These things fall automatically. You can do from here. And this will be quite a nightmare for this guitar, for these guitars, because one has a hole, another doesn't, one has strings. If you worked on meshing or you worked on mesh processing, you will not touch this problem because this is just too difficult. So how well does it work? I do want to remind you there's no training here, right? So this is like training. Okay. So again, I will explain the main things we're seeing here. So there are different methods, and ours, you see ours on the right. And there's two measures. One is accuracy, another is error. Seems like the same thing, right? Like very related, but it's just like fine details in this notion. Error is absolute error. Accuracy are done in sort of thresholded band, less than 2%, less than 5%. This is how these benchmarks are set up. And these are different data set. Tosca 1920, one has partial one has isometric variations. You would know this if you work in this data set. And ours is the only method which doesn't have any training. All these other ones have training. The WKS, which is a variant of HKS or heat kernel signature, does not have a training, but all the others have training. And as you can see that without any additional thing, we are already state of the art, but you can combine it with traditional methods. You'll get, in certain cases, slightly better. And this is kind of expected because ours, we're distilling from an orthogonal set of information, which is coming from images. And something like functional maps is based on geometry based. So you can try to combine them, and now it's combining two different sources of information, so there is chance that it will get improved. I think the next one I find more interesting. So as I said, these three are different data sets, so they have different characteristics. But what we can do is I can train on one of them and test on a different data set. Should not matter for us because we don't have any training, but it does matter for the other methods. And that's exactly what you will see. That ours consistently remains the same, where for the others, like if you train on Shrek and perform on Serial, the performance will degrade for the other methods. Sometimes they don't, but when we look back, then the data sets have substantial overlap. So it's again, again, many ablation one, but I want to highlight one thing. So this, again, this is a good summary slide for this part. This method, this texture was presented at SIGGRAPH last year. What it does is tries to find a consistent appearance on the whole model. But this is what I say, please don't do it, because that way I have lost the variance. If we keep it, which is ours, you see we have better results. So it's better not to do the projection. For free, we get segmentation. So what you can do is you can take the features, and we learned about k-means today morning. You can run k-means, you can run mean shift if you want. It automatically gives semantic segments. So it automatically gives some patches. And there doesn't have to be any sort of mesh feature between the paw and the leg, but it comes from the image side. So it's not visible in the mesh, but still gets picked up. Limitations, the big limitation is occlusion. Because we are doing this projection, if I have my hand here and this part is not visible from anywhere, no features is going to be projected here. And any data set bias we will have. Okay, so I come to the last part of the talk. I see why I'm confused, because my timer shows I've only used 30 minutes, but I had refreshed due to this technical glitch. More than 30 minutes. Okay, so here's a problem. Again, this is your favorite conference now, so this will appear there. The goal is I want to move things. The goal is I have this image, and I want to do image editing, but it has some effects here. So the type of editing I want to do is I want to move the lab from there to somewhere else in the table. Imagine how it will be. Okay. Yeah. And I don't know anything about rendering. How can we do this? And I'll explain this. But the main idea is, in many of these problems, if we go through the inverse rendering pipeline, this is just too hard. And we will run into ambiguities. We will need some priors. Here, we have the diffusion prior, which is going to help us, but we have to be a little bit clever how to use it. So that's the last part of the talk. Okay. There's two changes I made to the slides after Ruth's keynote yesterday. One you may have noticed. Space is now more. It's less crowded. And the other one, when I explain the results, you will see. Okay, so what's the problem setting? I have this image. I select an object, so always the mask is given. So the object mask is given. And I want to transform this, very much like the interactive images I showed. Same goal. I'm still working on the same problem. But I now want to do edits that are 3D edits. So if I move this cup closer to you, you see a perspective, or etc. And this is the result. And I want to create this result while preserving the identity. So I'll be a bit vague here. I would not say what identity means. I'll leave it to you. I'm happy to discuss it afterwards. So this is a result. And these pairs of examples are such that if you look, if I give you more and more time, you would see the differences more. First few seconds, it's going to be hard. So goal is we are going to preserve the identity, but at the same time, we don't do any training just because we don't have any training data. We'll come back to this again, and we want a positive output. But why is this problem hard? Because if I move this here, then if you look here, the shadows and everything changes a lot. This is what makes it hard. If I move a bird on the sky from here to here, this is maybe a lot easier. But if I move where the shadows are interacting, that's where here. The sand is particularly difficult because it has this one. Again, this type of table, I love doing this type of tables. But again, it's training free, no 3D data, and we don't have 3D edits. And I'll talk about some of these other methods later on, especially this object state. And ours doesn't require any 3D data, and it's training free. And it's the only one that supports really 3D edit. So let's start with some examples, and then I will explain. So I'll show 2-3 examples, and each time I'll give you some time. I move the toaster a bit to the right. You imagine how that it is? There's no underlying, we're not solving any of the investment rule. Okay? This is my favorite example here. I want to move the wine glass. You can see the refraction, you can see the thing. We saw some beautiful caustics today morning. And I want to move it in front of the. Sometimes, and we did really get confused during this paper, we had to come up with a naming convention because it was sometimes hard to tell which is source and which is edit because it's not that. Now I come to the second part, which I mentioned, that I learned yesterday from Ruth's talk is I could tell like which edits were harder versus which were easier, where you can tell it closer. But then I realized when we are moving the object, so every time I tell you the object, so I know you have the focus on the wine glass, so that's good. And I say I move it here, but then the changes by construction is happening near the glass. So the changes are very close to the window where it happens. So this is exactly the one we had yesterday where there was the airplane and the engine disappeared next to the people, right? So this is one of those cases where if the changes was far in here, if changes are happening here, that would be fine because it would be away from this. And that could have been fixed easily with some masking and other. But here, we want the change really where it's hard to change, and that makes the problem interesting. This is a real photograph. Here, this is a bit easier. You can see the crumbs changing. Okay. So object stitch is a method that allows you to edit. This is not our method. This is from last year's, where you can change, but there's no control on the final one. You say, okay, change, but with the position itself. So you don't have fine grain or any grain of 3D control. It is training based, so it is trained on many pairs of images. So not training free like ours. Ours, you'll see that the axis really maps. The one thing we don't have is how to transfer across images and leave it for another one. Okay, so how do we do this 3D control without having without having training data? Okay, so this is a part I will pause. This screen is okay, I just paused it here. So what we want to do is very much what we do in classical computer graphics. We move things and textures are associated here, textures move with this. We want to do this. But now we don't have a renderer anymore, we don't have a mesh anymore, etc. So what we have again is imprecise depth, what we have. But on the depth, I can have features. This is what we did in the second part of the talk, where I unprojected image features back onto this. So I can do that. I can move it. So essentially, I can find a very nonlinear warping of the image features from here to here, but not the image, the underlying diffusion features from here to here. And now I can pose that in this, so I know I want a diffusion image here, but certain areas I know what the features should be. And that's the optimization answer. So this is very hand-wavy, I wave my hand a lot, but I'll explain it a bit more here. So we start with an image. We run this, so we have to invert it. This is something you can know how to do this. Then two things happen. So we have the depth guidance on top, very much like loose control. Depth is estimated depth, not real depth. Okay? So that's the depth. And then we run it to get the inversion. This original image gives me certain activations. This is the features we have. Okay? Now the goal is, under the prescribed 3D edit, I have to reposition the features to certain locations. So the 3D edit specified. So D to D prime, which is what is the changed mask that I have, because I have a mask, I take those point cloud and move it here under 3D. This is like a direct 3D mapping. Question is, what happens to the features? This is what, if we are done, then we are pretty much done. So let me explain this, and it's super simple once you see it this way. I take the original features, I read it out. I lift the features from the image plane to the 3D because I have depth at the pixels. Then I transform them because I have the explicit transformation given. So I move the features in here, and you can imagine what's the next step. We project it back to the image plane. So we use the proxy depth to go from this to this. And the underlying features is exactly as I explained from the different levels of the UDEP. Okay, so we have that, and now we set up an optimization that these features are satisfied, give me an image that's plausible. No training required. You can see here, good. Here's another one, and you can see the errors here that you look at the number plate that changed because diffusion models are still pretty bad with text generation. This is a very nice example where we rotate the cup. This is Karan has had this coffee mug. We rotate it, we get here. Looking at the time a bit. So how do we go about doing this? You can do it in small steps, and you get kind of this animation, etc. We did. I'm jumping a little bit, looking at the time here. So we did like a user study to evaluate this, but then we came up with, why don't we set up a benchmark, and this is available for download. And I think this is useful to see the way we generated the benchmark. The synthetic renders. For the synthetic renders, we specified random object selection and rotation. We rendered these out. So this becomes our ground truth now. Right? And we are going to compare against this. So we release these data set you can compare again. We do this. On that synthetic data set, if you see ours, is still the best, without requiring any training. It is possible to fine-tune on the synthetic data, but I'm not sure if it will definitely improve this course, but not like beyond this. Okay. This is another very nice example where we move the vase from the top of the cabinet down onto the table, and this is the type of result you will get. We have various controls, additional controls that I will leave out. So what are the limitations? The main limitations, if you are still paying attention, you will understand depth estimations are bad, but then they are particularly bad if I completely turn around. And indeed, if you turn around this banana, this looks terrible, and of course the resulting thing is also terrible. Same thing happens here. If the depth estimations are wrong, there's nothing. But maybe the recent object recognition, or estimation priors. So I'll take maybe 2 more minutes to just show where we are going beyond this. I think the next thing beyond single images is single images with motion, which is called videos. If you take this one and imagine you thinking how this is the work we already published here. there's a lot of glitches you would see, but I think there's a lot of promise here. And someone mentioned this paper that has appeared recently, which is step-based, take this very coarse input video, and you produce a very fine input video on the spec. This happens to be our paper, so I know a bit about this, but I do want to say a couple of lines about this work as a lesson, and that keeps us very humble in some way. So the basic idea of this is we have multiple frames, so can we use a video upsampler and get the result? I'll play it one more time. You can see it. The web page is on top. You can try it. Please don't all try to correct. There's a lot of videos to look at. It works quite well. Now, we did a lot of fancy things at the beginning. We said, oh, let's be smart. Let's do this extra loss. Let's have this consistency loss. Let's do all these things. And then the student was brilliant, and he implemented all these. The results were great. And then we have to write the paper. Well, writing is, of course, you have to do the ablation study. And then we realized that these things are really hurting the method. So it turns out the best method, best as in, of course, the optimization gets better, but you lose its generality, you lose the diversity of the result. So sometimes it's good to have the simpler methods, and we should encourage the simple method rather than artificially making it complex. And if we had not done this ablation study, we wouldn't have realized, because I thought those were making the methods. And this is, again, working in this nonlinear space. This is inherent. So all the code and data you would find online. So what we talked about are 3 different representations. One is this very boxy representation for generation. I think cuboids can take us a long way. We showed this analysis one where analysis comes for free in certain cases. And here you can, the original representation doesn't matter, but you don't want to project the distribution, you want to keep the distribution. That's a key message. And then we say a lot can be done in terms of editing if the final goal is editing, right? If the final goal is in a video, maybe this is still possible. If the final goal is 3D, we have to do something more explicit, 3D and physically based. I have to do an advertisement here. So I hope you're really enjoying London. There is this event happening that Tobias and I are organizing in 25. This is called Eurographics. I think everyone knows. Please submit, and you need to know October 3rd. So before you go for your summer break, please submit, and then you can go on. So I did quick check. It's already good. The system is already up and receiving submissions. And we already have an amazing set of keynotes. I'll just leave the pictures because you would know all of them, so I don't have to mention who they are. With that, I will stop here and happy to take questions. Thank you.